light to 1 says that 3 times 10 to the 10 centimeters per second is equal to 1, or that 1 second is equivalent to 3 times 10 to the 10 centimeters. And this, in fact, is how length scales are defined in metrology today. They're defined in terms of time scales. Time scales are defined by the ticking of processes in atomic clocks. Length scales are defined by just saying that the speed of light is 2.998 and a bunch of other digits times 10 to the 10 centimeters per second. I assume that you feel comfortable with g equal 1, which I like to think of as saying g over c squared is 1, and that is 0.742 times 10 to the minus 28 centimeters per gram. So that says that 1 gram is equivalent to about 10 to the minus 28 centimeters. And I urge anybody who doesn't feel more or less comfortable with working in these kind of units to read and think about the table that is in the reading that I gave you in the section connected with Einstein's equations where this is discussed in some detail. So I'm going to then set this, Newton's gravitational constant equal to 1, and henceforth g without indices will be the trace of g mu nu. Okay. Now, because I have a system with weak internal gravity, it's also I'm going to assume then, well, you can show through the Einstein equations as we will work out their consequences, the waves are also very weak. So throughout space-time, the gravitational field is extremely weak. And so we can linearize in the strength of the gravitational field, or linearize around flat space-time. And so we can look at not just the full Einstein equations, but the linearized Einstein equations at first order in the perturbation of the metric. And so we write the metric as eta mu nu plus h mu nu in some gauge. And I have not yet specialized my gauge at all, except for the fact that I'm going to demand that the magnitude of the components of the metric perturbation is small compared to 1. Now I want to make a side remark that sort of motivates what otherwise might seem not a terribly useful thing to do. The Einstein tensor, g mu nu, of course, is the Ricci tensor minus 1/2 the Ricci scalar times the metric. And so the Einstein tensor differs from the Ricci tensor just by a trace, that is a scalar times the metric. And so we can think of, and R is this trace of the Ricci tensor. So it differs by the trace of the Ricci tensor times the metric times a constant. And it's interesting to look at then at the trace of the Einstein tensor. So I want to contract on the mu and nu indices. So g, by which I mean g mu mu, that will be equal to the trace of the Ricci tensor, which is R, the Ricci scalar, minus 1/2 R times the trace of the metric. Well, the metric with indices up and down is the Kronecker delta. And that is just 1, 1, 1, 1 with zeros. And so the trace is 1 plus 1 plus 1 plus 1, which is 4. And so it's the Ricci scalar, or the curvature scalar, minus 4 times 1/2 times R, so minus 2R, so it's minus R. So the trace of the Einstein tensor is minus the trace of the Ricci tensor, which says that then the full Einstein tensor is equal to the full Ricci tensor with its trace reversed in sign. So we call it, say, it's equal to the trace reversed Ricci tensor. You've just flipped the sign of the trace. But otherwise it's the same. You have subtracted off something that's proportional to the trace of R, where the coefficient is chosen so that the trace of G is minus the trace of R. Now, the Ricci tensor and the Riemann tensor are particularly simple when written in terms of the metric perturbation. In fact, it is that fact that's intimately connected to the fact that when we made a first guess at what the Einstein equations might be, our first guess was Ricci tensor is 4 pi times the stress energy tensor. That comes out very naturally. The Riemann tensor, whose trace is the Ricci tensor, it is something that is intimately connected with tidal deformations, and it is something that mathematically is intimately connected with a metric. And so it turns out then that if we want to work with the full Einstein equations with a source on the right-hand side like this, that the Einstein equations will take a simpler form, and one that will be mathematically more tractable to work with, if instead of writing the Einstein tensor in terms of the metric perturbation, we write it in terms of the trace reverse metric perturbation. I want to do to the metric perturbation the same thing as one does to Ricci in order to get Einstein. So this is a very arm-waving motivation for what I'm going to do. Okay. So I'm going to introduce then the trace reversed metric perturbation, which is then the metric perturbation, this guy, minus 1/2 h times eta mu nu, where h is the trace, it's h alpha alpha, or it's h alpha beta, eta alpha beta, where throughout here now I'm doing everything to first order in h, and so I'm pretending mathematically that h is a field that lives in flat space-time. All the mathematics is flat space-time mathematics on the metric perturbation. So I introduced this simply in order, in the end, to make the Einstein tensor and the mathematics I'm dealing with look particularly simple. When I do that, then it is a straightforward exercise from the mathematics that you have already done for getting the Riemann tensor in terms of derivatives of the metric, which would then become derivatives of the metric perturbation. To go from there to the Ricci tensor in terms of derivatives of the metric perturbation. To go from there using this to the Einstein tensor in terms of derivatives of the trace reverse metric perturbation. So that's straightforward mathematics, and the bottom line is that the Einstein tensor, and I'm going to write it as twice the Einstein tensor because it looks simpler that way. Twice the Einstein tensor is minus h bar mu nu, comma alpha alpha, minus eta mu nu, h bar alpha beta, comma alpha beta, plus h bar mu alpha, comma nu alpha, plus h bar nu alpha, comma mu alpha. Okay. Let's just look at these terms for a moment. The first term is really a wave operator. That is, it's two derivatives and contracted. So it's a wave operator acting on the trace reverse metric perturbation. So that's the kind of thing we would like to see. But then I have three remaining terms, which R is required symmetric under the interchange of mu and nu, since the Einstein tensor is symmetric. There's an eta, the mu and nu indices on eta here, that's symmetric. And in these two terms, it's one with the mu before the comma, the other with the nu after. Here the nu is before and the mu is after. So this is just symmetrizing this remaining term. And twice the Einstein tensor must be 16 pi times the stress energy tensor. And so this is Einstein's equations linearized about flat space-time. Now I want to compare those with the corresponding electromagnetic case. The comparison with electromagnetic theory is often very useful in sort of getting oriented in doing the mathematics of general relativity. So, in electromagnetic theory, if you go through the same process, you define the electromagnetic field tensor in terms of a vector potential A beta comma alpha minus A alpha comma beta. And then you look at the Maxwell equation that says F alpha beta comma beta is equal to 4 pi times the charge current 4 vector. This automatically guarantees the other Maxwell equations. So I'm assuming for the moment that you have seen Maxwell's equations in terms of tensors. Some of you may not have. And so if you haven't, then you can relax and ignore this at this point, but you should go learn that sometime soon. If you just plug this expression in for the electromagnetic field tensor, that gives you the following in a straightforward manner, that minus A mu comma alpha alpha plus A alpha comma mu alpha is equal to 4 pi J mu. Okay. So that's Maxwell's equations written in terms of the 4-vector potential. You recall that I talked earlier about the fact that the electromagnetic field tensor is an analog of the Riemann tensor. And the 4-vector potential is an analog of the metric perturbation, or the metric. You differentiate the vector potential to get the electromagnetic field. You differentiate the metric perturbation twice to get the Riemann tensor. Okay. So there's an analogy. It's by no means a perfect analogy. There's also a close analogy between this form of Maxwell's equations and the linearized Einstein equations. And in the Maxwell equation case, there's a standard way to deal with this to bring it into a form where it's easy to solve Maxwell's equations. You introduce Lorentz gauge. And this Lorentz is different from the famous relativity Lorentz. The relativity Lorentz has a T in here, and this Lorentz does not. A fact that escaped the authors of Misner, Thorne, and Wheeler 30 years ago, and they have been embarrassed by multiple people pointing it out. Okay. Okay. Lorentz gauge is a gauge in which A alpha comma alpha is equal to 0. That is, A is divergence free. And you can make a gauge transformation. I talked already about gauge transformations that will get you to Lorentz gauge. Up here, that will make this term vanish if we commute those derivatives. And we can do it in flat space. These are partial derivatives, in fact, in a Lorentz coordinate system in flat space. They commute just fine. In curved space-time, what we would have if we did the same thing, there would be a semicolon here, a semicolon there. We would be taking gradients, and we would be having to commute a double gradient. That commutation of the double gradient would bring in a term that is a Riemann tensor contracted into the vector potential. I think it becomes in the end a Ricci tensor in the final end. I've forgotten for sure. So there will be some curvature coupling that comes in curved space-time, but I'm not worrying about that. I'm in flat space-time, so we don't have to worry about that here. And so I can introduce Lorentz gauge, and I can commute the double derivatives. When I do that, then the term here goes to 0, and Maxwell's equation just reduced to the flat space wave equation with a minus sign, A mu, by which I mean A mu comma alpha beta, eta alpha beta, or I mean A mu comma alpha alpha, all just notation for the same thing, that is equal to 4 pi j mu. So that is how we proceed with Maxwell's equations. And we get in the end a simple wave equation for the components of the vector potential where the source is the charge current 4 vector. And so that motivates what I'm going to do in the case of Einstein's equations. For Einstein's equations, I have a term that is a wave operator, so this is the kind of a term I want. I have a source term on the right-hand side, and you notice all three of these other terms, they involve divergences. It's a divergence on alpha and on beta here. If I commute derivatives, then this will be a divergence on alpha, and if I commute derivatives, this will be a divergence on alpha. So, in the gravitational case, I'm re-emphasizing this is for weak waves in flat space-time. Negligible self-gravity in the source, so it's a very special case that in fact is not the case we really deal with in the real universe. But in this case, then I want to introduce gravitational Lorentz gauge. That is the gravitational analog of Lorentz gauge, which is a gauge in which h bar alpha beta comma beta is equal to 0. And then I want to commute the derivatives, which I can because I'm working only to first order in the deviations from flat space-time, and so I'm doing things mathematically as though I were doing field theory in flat space-time. When I do that, all three terms here, all three terms go to 0. And the Einstein equations reduce to minus the flat space wave operator acting on the trace reversed metric perturbation h bar mu nu is equal to 16 pi times the stress energy tensor. So everything goes through just like it does in the electromagnetic case. The difference is that the gravitational field is described by a potential, the trace reverse metric perturbation, that is a second-rank symmetric tensor instead of the electromagnetic case, where the electromagnetic potential is a vector field. Here it's a tensor field that's symmetric. The second difference is that whereas the source up here is the charge current 4 vector, down here it's the stress energy tensor. But aside from that, everything goes through just fine. And so then, appealing to our experience with electromagnetic theory, we know how to solve this wave equation. We can solve the wave equation using the standard Green's function, which tells us then that h bar mu nu is equal to 1 over 4 pi. It's equal to, is it 2? The factor, I suddenly can't be absolutely sure of the factor. It has to be 2, isn't it? Or is it 4? I don't even have it down in here. It's a 4 pi in that case, so it has to be a 4. H bar mu nu, well, let's remind ourselves, in the electromagnetic case, the solution is that A mu is equal to the evaluated time t in location x is equal to the integral of the charge current 4 vector evaluated at time location x prime, and at the retarded time, t prime is t minus the distance between the source point and the field point, divided by the distance between the source point and the field point. So we have our source here. The source point is x prime. The field point where we're evaluating the field is x. And the distance between those is x minus x prime. And we have to integrate over source points of j mu at this retarded time divided by the distance between the two points. And so similarly, by the same mathematics, but differing by a factor of 4, because this is a 16 pi and that's a 4 pi, we have h mu nu at time t in location x is an integral of the stress energy tensor at x prime at retarded time divided by x minus x prime. And we're integrating over Cartesian coordinates in three-dimensional space. So that is one way to write down the solution. That's the most familiar way to write it down for most people. Okay. Now I want to emphasize something. This is in Lorentz gauge, that is true. But this Lorentz gauge is not generally TT. Even though the waves are propagating with the speed of light with respect to the coordinate system, as you see from the fact that it's the wave equation acting on h bar is 0 in vacuum. The waves are propagating at the speed of light with respect to the coordinate system, which is what happens in TT gauge. In TT gauge, the waves propagate with the speed of light. Nevertheless, when you look at this closely, you discover that although in both cases the waves propagate with the speed of light in the coordinate system, this is not TT gauge in general. And so then the question arises, well, how do you get to TT gauge then? How can you most easily get to TT gauge? So I want to ask this in the following manner. Suppose, in general, we are in a gauge where the metric perturbation, trace reversed, propagates at the speed of light. Then how do we get from there in the fastest and quickest and easiest manner possible to TT gauge? We've got to do a gauge transformation. Now I'm going to answer this by specializing to the situation that we will essentially always encounter, where we're dealing with the wave that is propagating with phase fronts that are very nearly planar in the sense that the distance between crests and troughs of the wave, a wavelength, is very small compared to the scale on which the wave front curvature changes or direction changes. So I'm going to approximate to the case where I have a locally plane wave. And that's essentially always the case in an astrophysical situation where you're well outside the source. The wave is locally plane. So I want to get to an answer very quickly. So for a plane wave, and as soon as I've said it's a plane wave, then I can let it propagate in the z direction. I can choose my axis so it propagates in the z direction. Then in this gauge, h bar alpha beta is a function of t minus z and doesn't depend on coordinates in any other way. Because it's assumed to be propagating with the speed of light. I've said it's planar, I've approximated it as planar, and then I've chosen my coordinates, so it's propagating in the z direction. That means that the metric perturbation itself, which is the trace reversal of the trace reversed metric perturbation. That is, if you want to get back to h alpha beta from h bar alpha beta, you just have to reverse the trace again. Okay? So that means that the metric perturbation also is a function only of t minus z. Okay. And so it is an exercise that I will give you to show that in this case you can get to TD, well, you're asked to find how do you go to T gauge, and the answer is you use a gauge change generator. You remember the gauge changes are generated by some vector field, C mu, that also is a function only of t minus z. So it's a special kind of a generator that, like the metric perturbation that you begin with, is a function of t minus z. It propagates, quote propagates, with a speed of light. It's not a physical thing, it's just a ripple of the coordinate system. You're putting a ripple into the coordinate system that propagates with the wave in the same direction with the same speed. Okay. So I'm asking you to show that you can find a gauge change generator, C mu, to get to T gauge. And when you do, the result is that H, J, K transverse traceless. Let me start over again. The result is that H, in this gauge then, that H00 after the gauge transformation, H bar 00, H bar 0J vanish, and also H00 and H0J vanish after the gauge transformation. And HXY, let me just back up. I've got to say, let me start over again. I want to do this very carefully. We know this is always true. We're now in TT gauge. We've somehow gotten there. And so in TT gauge, that's always true. And so you have found a way, by a gauge transformation, to get rid of the temporal and the space-time parts of H bar, and of H similarly. And then HXY TT, which of course has to be HYX TT, is identically equal to this same HXY HYX that you had in the original coordinate system. The same ones as we had to begin with. And it is also true that let me come up here, HXX TT is obtained by taking the HXX of the original coordinate system with a bar on it, if you wish. Let me back up. This is true with bars on. It's also equal to HXY without bars on. Because since H bar and H differ by a trace, the off-diagonal terms are the same whether you've got a bar on or not. Okay. HXX TT, let me write in terms of the H without a bar on it from the original coordinate system. It's equal to HXX minus 1/2 HXX plus HYY. That is, it is the original H with the trace removed, which is the same thing as just 1/2 hxx minus hyy. Hyy is equal to the original h in the original coordinate system, yy, minus, with the trace removed, or equivalently it's 1/2 with a minus sign, hxx minus hyy. And so let me box these in and talk about them. So this is the result of the calculation. Now this result is really very simple. It says that this gauge change, to get to TT gauge from any other gauge where you have a plane wave propagating in, say, the z direction, all you do is you throw away the time, and time-space parts of the metric perturbation or the trace reverse metric perturbation. Just throw them away. You just make it purely spatial. And then for the spatial part, I should have said you also throw away the longitudinal part, zj, that is, anything that has a z in you throw away. So you keep only the pieces that are transverse and spatial. And with them, the off-diagonal parts are unchanged. And the diagonal parts are obtained just by removing the trace for the transverse parts. So it's trivial. Once you've been through and proved this theorem, you have a very powerful calculational tool. So to compute the TT gravitational field, if you're already in any gauge, such as this one, where the waves are propagating at the speed of light, you go up there, orient your axes so the waves are propagating in the z direction. We have approximated the phase fronts as flat so I can do a planar discussion. And you just throw away the temporal part of the metric perturbation, you throw away the longitudinal part of the metric perturbation along the z direction. You keep the transverse spatial part, but you just remove its trace, and you're done. It's almost trivial. And so let me give you an example then, which is the example that one uses in practical computations for something such as this. Example, suppose that I have my source, it's emitting waves. I get out here far into the wave zone around this source. This is many wavelengths away from the source. The phase fronts look like this. They're very nearly flat. And I simply introduce spherical polar coordinates in here centered on the source. So I have spherical polar coordinates r, theta, phi, the usual spherical polar coordinates. And I go out here to a point where I want to evaluate the gravitational wave field. I want, at this location, h, j, k transverse traces. I go here and I introduce a local Cartesian coordinate system with one of the axes pointing along the radial direction and the others transverse. And I look at basis vectors there. And the radial unit basis vector, which would be the z basis vector if I'm in the notation I used over there, it's ER hat to this coordinate system. It's the unit radial basis vector. And this should be in that direction. This is like this. So the basis vector in this direction is E theta hat. The basis vector in this direction is E phi hat. And these form a local Cartesian basis, the unit vectors in the radial, the theta, and the phi directions. I have computed the components of the metric perturbation using this formula in my Cartesian, in my spherical polar coordinate system. And so I presume that I then know here, using the formula in terms of the integral over the source, I know h j k with hats on it, the components of the metric perturbation in this basis. Then I want to know the gravitational wave field. I want to, or I know it with a bar on there. I want to know what it is what is the transverse traceless gravitational field. And I know that the only components will be in the transverse direction, the theta direction and the phi direction. I know furthermore then that h theta phi is just going to be equal to h theta phi that I have computed using the source integral. It's unchanged. H theta theta will be equal to 1/2 h theta theta, transverse traceless, 1/2 h theta theta with hats minus h phi phi with hats. That's what I do get when I do the trace reversal. And h transverse traceless phi phi with hats will be minus this same thing. That's what I get when I do the trace reversal. So all I've done, I've just thrown away all pieces of my source integral, except the pieces in the transverse direction, and then I have removed the trace. And since h bar and h differ only by a trace in the first place, I can do this equally well on h or on h bar. This will be h, the same thing as h bar theta hat phi hat. This will be the same thing as 1/2 h bar theta hat minus h bar phi hat phi hat. They differ only by a trace, so I can just do this process of throwing away everything except the transverse part of the field and then remove the trace. I can do it equally well on h bar or on h. It doesn't matter. So this is a very important computational tool. It enables you to fairly quickly compute gravitational waves where you just do the source integral and then project out in this manner, pick out the gravitational wave field, the transverse traceless part of the gravitational wave field. Okay, there are a lot of things I've asserted in the lecture on Monday and today that are exercises for you, but that's going to be the nature of much of this course. I want to talk about the basic ideas, the basic results, the consequences, and leave the details to you. I think you have the tools to be able to work through as many of the details as you choose to or have time to or is useful for you. Okay, thanks. I'll see you on Monday. No.
That's the solution for the trace reverse metric, right?
Yes, yes. An error, by the way, an error here, this should be h bar. Okay. However, when you project out the TT part, it doesn't matter.